many of you know, states that energy cannot be created, nor can it be destroyed, but only transferred and transformed. Now, taking electricity down to the basic element, or the starting point, we need to begin with the atom, which is the building block of all matter and the place where our electricity story really begins. Now, looking more closely at the atom, you see it is composed of the nucleus, which consists of protons and neutrons. And then swirling around the positively charged nucleus, we have electrons, which are negatively charged and potentially in balance or electrically neutral because of an equal number of protons and electrons. Now, however, these electrons can be knocked out of their orbits fairly easily, and when this happens, then they're referred to as free electrons. Now, when this occurs, the balance ends, and the atom becomes positive, seeking a negative replacement. And for our purposes today, this movement of electrons through a metal conductor or a wire is called current flow. Okay, enough of the minutiae. Now let's get into a little historical background. Thomas Edison, pictured here, is where we'll start. And he was the founder of the Edison Electric Company back in 1878, and probably was best known for his invention of the electric or incandescent light, though he was also the inventor of the electric phonograph, motion pictures, the electrographic vote recorder, and the magnetic iron ore separator. So he was a real genius for sure. Now, the other gentleman pictured here on the right is Nikola Tesla. Certainly not as famous as Edison, although there's an electric car right now being designed and built in his name. But he's equally important in terms of inventive genius. Tesla worked for Edison in early 1884, then left after a relatively short time to pursue a competitive interest. And that was the best way to transfer electrical energy. Now, Edison was a big proponent of direct current for electrifying America and electrifying the world because he felt it was safe to generate, transmit, and use, and very economical for the customer as well. The DC power was produced using a steam-driven turbine driving a generator which used brushes and commutators to operate, and as a result, it was fairly complex and difficult to maintain. Now, Tesla, on the other hand, was a big advocate of alternating current, AC power. And this was the reason he and Edison separated, neither one wanting to give up on the idea of which power source was the best. Now, similar to Edison, Tesla used a steam-driven turbine to drive the AC generator, or the dynamo as he referred to it as, and this converts mechanical energy into electrical energy, as you know. And it consisted of a rectangular coil of wire rotating in a uniform magnetic field, and the magnetic field was derived from a permanent magnet which was surrounding this rotating coil of wire. As Edison's incandescent light bulb became more known and the word spread, the shark financiers, if you've got anybody out there watching Shark Tank, a popular TV program now, well, the shark financiers of the day back in the 1800s got wind of it, of Edison's light bulb and DC current, and they saw an opportunity to get very rich with the idea. Now, one of the first to approach Edison was J.P. Morgan of equity investment and banking fame, and then a bit later, Cornelius Vanderbilt of the railroad and ocean shipping fame got involved. And they all knew there were other competitive threats out there, and it was imperative that money be invested in the promotion of this concept, not only the light bulb, but the energy source which lit it, the DC power. Now, one of the first demonstrations was the electrifying of Thomas Edison's house in Menlo Park, New Jersey, and hundreds of people came, and they were just astonished at this miraculous invention. And then next came the electrifying of the steamship Columbia with its integrated DC generator, which was providing the power for all of the lighting needs on the ship. So DC power was getting some real attention. Now we move back again to 1884, and Nikola Tesla, the advocate for AC power, was now being joined by another investor, another shark, George Westinghouse, because he was a real believer in AC power and because he'd already licensed the rights to Tesla's patented AC induction motor and transformer. So a battle was forming between these two entrepreneurs and their financial backers, and it was called the War of the Currents, pitting DC versus AC power, and Edison claiming the extreme danger of AC power, even electrocuting elephants as a public display of his particular position, and Tesla providing the opposite view with demonstrations on how benign AC power was compared to the DC if it was properly handled. Well, the proof in the pudding came in 1893 when both sides bid on the project of lighting the World's Fair in Chicago. Tesla Westinghouse came in and won the bid because they were 30% less than Edison and Morgan. Then a short time later, a project to electrify the city of Buffalo, New York, using hydroelectric motive power derived from Niagara Falls was awarded to the Tesla Westinghouse team. And again, it was primarily for economic reasons. Because of the intrinsic limitations of DC power and its inability to travel long distances without increasing the number of generating substations. AC power, on the other hand, had much more flexibility in this regard, and with the ability to electrify all the way to the Mississippi River with a minimal number of generating stations. So it was becoming clear just before the turn of the 19th century that AC electrical power was the answer to the lighting of our homes, factories, and streets. And that was much to the dismay of J.D. Rockefeller, who had been benefiting handsomely by selling kerosene lamps for illuminating various purposes all across the country. Okay, enough of the history of how AC power came about as the primary current supply in our country. Now let's explore the differences between these two power sources, AC and DC, before getting into AC power specifically and how it is distributed and applied in a boiler circuitry. First of all, any electrical generator, be it AC or DC, needs a motive force to drive the generator to produce the current. And that could be a steam turbine, a gas turbine, a wind turbine, or hydropower, as was used by Tesla in electrifying Buffalo. So we have the motive force driving an electrical generator. Now let's look at how the generator works. The DC generator consists of several essential parts. First, a magnetic field, which is denoted on the screen by N and S. Then it has a coil. It has a half-ring commutator and carbon brushes. Now, as the copper wire windings, which is the conductor, turn in a clockwise direction within the magnetic field, electrons are separated from their atoms, creating an electronic flow as they seek balance. Now, this is current flow, which alternates every half turn as the coil spins at about 3,600 RPM. Now, this action also sets up an electromotive force, or EMF, which is the force moving the current through the wire windings. It is the split ring commutator and the carbon brush which then unify this current into what is referred to as unidirectional flow. DC current is unidirectional flow, meaning the current only travels in one direction, as indicated by the clockwise direction in the diagram with the light bulb illuminating. Looking now at AC power generator, it looks similar to the DC version minus the commutator and including two slip rings to accommodate the alternating current flow. In these generators, as the coil within the magnetic field rotates at a high speed, again at 3,600 RPM, this changes the polarity and magnetic flux, along with the current and electromotive force, which are changing what we call sinusoidally, as depicted in the diagram in the upper left-hand corner of the screen right now. That's alternating current, and it's what powers our homes and factories and everything. Now, note in this picture how AC current flows simultaneously in both the blue and the red wires, and alternates in both directions as the voltage rapidly fluctuates between 0 voltage and full voltage, while moving between plus and minus with the reference to the horizontal, or I should say with reference to the horizontal line. So with this happening, why does the light remain lit constantly? Well, these cycles are occurring 60 times per second, so it's invisible to the naked eye. Okay, so why did Tesla win with AC power over Edison's DC power? Well, the main reason was economics. And without getting into the theoretical weeds with somewhat complicated formulas by Ohm and Joules, it boiled down to the fact that any time current flows through a wire, there is going to be resistance resulting in a voltage drop or a pressure drop. The smaller the wire, the larger the drop. Just like pressure loss in a steam pipe as steam flows from A to B. The smaller the pipe, the bigger the drop. So I either increase the pressure or increase the size of the pipe to reduce the pressure drop. Looking now at the diagrams on the screen, you see we have an electromotive force or voltage of 480 for both our DC and AC power stations, and we deliver 100 amps of current to our plant, which is 1,000 feet away. Now here's the problem. Remember I said that when current flows through a wire, we will incur resistance and voltage drop, regardless if it's AC or DC power. The problem with DC power is it is unidirectional flow, which cannot be transformed, meaning we can't boost it, we can't boost its electromotive force. This means we have to increase the wire diameter to reduce the resistance and put in additional power stations to get the current to the plant facility. Now, AC power, on the other hand, can be transformed. It can either be increased or we can decrease the electromotive force, boosting its power initially from, as you can see, 480 to 4,800 volts on the bottom there, delivering 10 amps to another transforming station 1,000 feet away, where we transform again, reducing the EMF from 4,800 volts to 480, and thereby deliver the 100 amps of current to my plant. This saves copper wire costs because of the smaller wire gauge and no additional power stations needed as would be with the DC power. That's how Tesla won. And that's exactly what you see here, with a large transforming station taking AC power and increasing the voltage, or the EMF, transmitting it across power lines to the pole with a transformer, which reduces the voltage to what is required in this house. So, is DC power used today? Well, as I'm sure all of you know, it is. And it's in our cars, it's in our telephones, it's in our smartphones, and it's essentially in all of our electronics. And that's because if we're not using batteries, AC power can be easily converted to DC power through rectification. And that would be using things like vacuum tube diodes, mercury arc valves, copper and selenium oxide rectifiers, and so on. All right, I think that's enough about DC voltage and how AC and DC voltage is generated and the differences. Now let's spend the rest of our time on AC voltage. And we'll start with some basic definitions and concepts for better understanding, beginning with ampere. It's the flow of an electrical charge from 1 ohm of resistance by a force of 1 volt, or the electromotive force. And then we have current, which directly relates to amps because it's the electrical flow measured in amperes. We have watt. That's the total power of a circuit at any given moment. So we have volts, which would be many times represented by the letter E, but volts times amps equals watts. A kilowatt is 1,000 watts. Hertz, it's the unit of frequency equaling 1 cycle per second. As I showed you or mentioned before, 60 cycles per second in this country, 50 cycles is often used in Europe. Voltage, it's the electrical potential difference between 2 points, also referred to as the electromotive force, EMF. Ohm, resistance overcome by 1 volt pushing 1 amp. Ohm's law, the electric potential difference between 2 points is the product of the current, amps times resistance equals voltage. So E equals amperage times resistance, I times R. Single phase, the distribution of alternating current where voltages vary in unison. What's three-phase? Well, it's a polyphase system for large loads. Voltages reaching peak values, but they do it sequentially, not in unison. What's a ground? Well, oftentimes confused with neutral. Ground really is a direct physical connection to Earth, and it's for safety purposes. And it should not carry current unless there's a problem. And neutral, it's known as common. It completes the circuit, allowing current to flow back and forth within both the neutral and the hot wire. Now, normally when I go through the electrical definitions, there's most always some confusion on three-phase versus single-phase power. So I thought if there is some now, this visual might help clear it up. Looking at three-phase power on the left, you see what I meant by polyphase, with 3 separate power supplies coming into a single connector, and then a common neutral wire, which is why we refer to this as three-phase 4-wire. Note also how the 3 current supplies have the same sine wave, but reach their peak values sequentially. Referring to the single-phase power supply on the right, you find 2 wires with a hot red wire and a neutral coming into the motor's starter, and showing a single sine wave where the power is moving through the hot and neutral wires in unison, thus the single line waving equally above and below the 0 voltage line. All right, there's just a couple more things I'd like to review before getting into the boiler circuitry, and that's just a brief review of some basic electrical circuits, and then the most common devices that we'll be encountering in the electrical scheme. Now, on the screen now, you see a series circuit with 3 electric lights, each of which creates their own resistance. And you can see 100 ohms, 300 ohms, and 50 ohms at the bottom there. Now, in the example, I'm referring to lights as causing the resistance within the circuit, but these resistances could also be caused by switches, by relay, coils, starters, and so on. Anything that impedes the current flow. Looking now at Ohm's law, you see we solve for the voltage requirement by taking the amperage in the circuit and multiply it by the resistance, which in this case is 450 ohms, 100 plus 300 plus 50. But what's the amperage? Well, to find that, the equation becomes I equals V/R, or voltage over resistance. In other words, take your known voltage of 9 volts and divide it by your resistance total of 450, equaling 0.02 amps. Now, to check our answer, let's find the voltage, which says it equals amperage times resistance. So I take 0.02 times 450 equals 9. All right, that's a simple series circuit. Now, what about a parallel circuit? Well, it's a bit more complicated, and we begin by understanding the basic rules for calculations within parallel circuits. First, and they're listed up on top there, the total current running through is the total of all the individual circuits. Second, the voltage across each path is the same. And the third, the total resistance in the parallel circuit will always be less than any individual circuit. Okay, with these points in mind, here in this example you see we again have three lights, each of which has a different voltage drop or resistance of 10, 2, and 1 ohm. We also have 9 volts of electromotive force, the voltage. Now let's again determine the amperage or current flow, and then solve for the total resistance in the complete circuit, keeping the rules for parallel circuits in mind. So to determine the current flow in amps, we need to return to the formula that we used before, I equals V over R, and compute each circuit. This gives me 0.9 amps, which is 9 divided by 10 in R1, 4.5, 9 divided by 2 in R2, and 9.0, 9 divided by 1 in R3 for a total of 14.4 amps. I can now solve for the total resistance in the circuit by using the formula R equals voltage divided by amperage, meaning I divide 9 by 14.4 equaling 0.625 ohms of resistance. Then if I want to check this and solve for voltage, my formula is V equals I times R, meaning I take 14.4 times 0.625 equals 9 volts. Simple, right? All right, enough of that. Now let's move to some of the common devices you're going to find in an electrical boiler circuit and basically what they do. Now, on the screen now, you see a starter and a contactor. They're often confused. The contactor on the right controls electrical power to a device, normally a fractional horsepower motor, so they either establish or interrupt power in the circuit. The starter actually includes a contactor, and as such, powers and depowers a motor of various horsepowers. And unlike the contactor, it also includes overload protection if the circuit overheats because of too much current draw, breaking power and then protecting the motor. So that's the difference between the starter and the contactor. Now, next we have relays and timers. The relay is nothing more than an electrically operated switch, and what you see pictured here is an electromagnetic type. Note the copper coil on the left. They are used when it is necessary to isolate a circuit or circuits until it or they are to be energized. Now the timing switch is used when there is a point in the operating sequence where a certain amount of time must elapse before a function is called for, and a corresponding switch would then be made to allow current to flow. For instance, if we are going to be timing out a pre-purge before we have trial for ignition, and we'll go through that a little bit later. And here are electrical transformers, which, as I mentioned before, can either increase or decrease alternating current. Now, the examples for reducing current are the 220/120, so we're taking 220 volts and reducing it to 120 volts. And then we have the 120/24, which is 120 volt single phase, taking it down to 24 volts. Then the 10,000 volt transformer, now it goes the other way. It boosts voltage, and in this case you're looking at an ignition transformer for lighting a pilot in a boiler. All right, the last device that I wanted to show you today is what is referred to as the BMS, or the Burner Management System. It's also called a programmer and sometimes a flame safeguard. And as you can see, it's gone through quite an evolution in its design over the years, viewing from left to right, but its functionality has never changed. It has always automatically sequenced the operation of the boiler's burner and all of its safeties. And as such, I kind of like to refer to it as the boiler's switchman. as it's only when the proper track is set in place that the train goes in the proper direction and therefore avoids unintended destinations or a devastating head-on collision. Now, in the case of the burner management system, it is sequencing the operation of the burner as it switches from operation to operation, from trial for ignition through burner shutdown and post-purge, while also monitoring all the safeties. So it's really a switchman and a train engineer all in one. And looking at this schematic wiring diagram of the boarder, which includes both series and parallel circuits, I call your attention to all the circles with numbers inside, which I have red arrows pointing to many of them. Now, these are all contacts in the BMS, which need to be energized in the proper sequence for the boarder to operate properly and safely. If they aren't, the boarder will not progress. It'll shut off. It'll lock out. Now, you'll also note the diagram is marked top and bottom. Now, this is only for fitting this diagram on one slide. In reality, this is either a B, C, or a D size drawing with what is shown as bottom all integrated with the top. So it's just one common drawing. And also note that the hot side is on the left of the diagram and the neutral is on the right. And remember, too, that AC current will travel back and forth through both of these. And here is the burner management sequence of operation, which one needs to know in order to understand how to read the boarder's schematic wiring diagram, regardless of whose boarder it is and whose wiring diagram it is. For instance, the first thing we need is AC power to the boarder's hot and neutral sides. And in this case, it starts with power being applied to circuits 4 and 5, noted in black at the top of the sequence. Now, referring to the electrical diagram again, you see where the main power is entering as 440-volt, three-phase, 60-cycle, from which we take a single-phase leg off and run it to our control circuit transformer, which is now reducing this voltage from 120-volt single-phase to 220-volt single-phase, I should say, to 120-volt single-phase, and then giving me 120 volts of power, which the BMS recognized by recognizing current at L2, which is circled in green. Next, we need to prove power again at terminal 4 in the BMS. Note the red arrow pointing to terminal 4. And now I'm also going to close the burner switch, which I've enclosed in the red box. This is a manual operation, which allows current to flow to my entire burner circuit, starting with the limit circuit between the two green arrows, and so marked limit circuit. Assuming there is a load, meaning the system is calling for steam or hot water now, the BMS is now looking for power at terminals 4 and terminal 6, which means in addition to the burner switch being closed, all the switches in my limit circuit are closed as well. And this includes my operating limit control, my high limit control, my main and auxiliary low water cutoff. Those switches are closed. And in the case of burning gas, my high and low gas pressure switches are closed. Look at the rectangular outlined area there. Next, we look for power at 4 and 20, our pre-ignition interlock circuit. And what this proves is that our main gas valve is indeed closed and not allowing gas to leak into the burner, causing a very rough pilot light-off, very dangerous. And it's accomplished using an end switch in the seat area of the valve, confirming closure, and then powering terminal 20. If that's not powered, we won't progress, we'll lock out. All things being good to this point, it's time to start the burner's blower motor for providing pre-purge and combustion air. And as you can see, we're looking for power at terminal 5 of the burner management system. To accomplish this, we need to energize our blower motor starter relay, which I've denoted with the the arrow on the right encircled in green. This then pulls in the starter for the three-phase 440-volt blower motor, noted that at the top left of the diagram, and it's got the red arrow. And at this point, terminal 5 in the BMS is energized, meaning we know we have power to the starter. Next, we want to energize our modulating damper motor circuit, which controls the flow of air to the burner based on the firing rate as dictated by the modulating pressure or temperature control on the boiler. Now, this involves the interaction of terminals 13 and 14 in the burner management system with other switches in the motor. And through this switching, proving the damper is in the closed or low fire position. In the diagram, I've highlighted the terminals with arrows and have also red boxed the damper motor 120 to 24 volt transformer, which means this motor operates, as you can see, on 24 volts and not 120. Proving the damper is in the low fire position because of the low fire switch that I've highlighted with the green circle in the damper motor, that then allows the closure of terminals 13 and 14 in the burner management system. We now want to drive the damper full open and begin a timing for pre-purge, which is in the 90-second range, a minute and a half, to allow for at least 4 air changes in the furnace before starting the ignition sequence for piloting. To prove this function of the full damper in the open position, we need power at terminals 13 and 12, and I've again green circled the high fire switch in the damper motor, which needs to close for these terminals to be energized. Next in the switching sequence, we need to prove we in fact have combustion air to support the burner's pilot in the main flame, and this requires proof at terminal 7. Note the circled combustion air proving switch, which would be mounted in the burner's wind box and needs to close due to air pressure for terminal 7 in the BMS to energize. Now, before starting the flame ignition sequence, we need to prove the damper is again back to the low fire position for light off. And this means proving terminals 13 and 14 again in the BMS. Note the low fire switch that I've circled, which again needs to close to allow this to happen. At this point, we're now ready for trial for pilot ignition. To do that, we need to energize our 10,000 volt transformer and open the gas pilot valve. Note the green circled area, which also energizes terminal 8 in our BMS. Now, immediately following this, we prove pilot for 10 seconds using a lead sulfide or a UV scanner, which energizes terminals F and G in the BMS. Now here you see the flame scanner in terminals F and G, which need to be energized before proceeding any further, otherwise, again, another lockout. Now, proving we have a strong pilot, we now move to opening the main gas valve, or the valves, energizing terminal 9, and during this time, the pilot stays lit while the flame scanner also proves the existence of the main flame. Now, as you can see with the green circle, this procedure involves the use of a parallel circuit, including the powering of 3 gas valves, 2 main gas valves, and a vent valve in between, which will be powered closed when the main valve opens. And you'll also see we power a light, which denotes the main gas valves are open, that in addition to powering terminal 9 in the BMS. Okay, now we have fire in the hole, and everything is in a safe operating condition, and the BMS, or the Switchman, is ready to turn the boiler's operation over to the modulating pressure control mounted on the boiler and sensing pressure or temperature, and thereby responding to load changes within the system. And as you can see, this involves powering terminals 13 and 15 in the BMS. Note the arrows denoting these terminals, 13 and 15, and the circling of the modulating control denoted as MC. That's now taking over the operation of the firing rate. And with the boiler now safely running and the BMS is in the ready to sense any fault condition, would then enunciate these faults and alarm them through circuit 3. And depending on the fault, shutting the boiler burner down. Here, let me show you an example of how this would work with a low water failure. Now here you see the red highlighted wiring when operating normally with the low water cutoff, green circled, closed, denoting a safe water level exists. And suddenly, the low water cutoff switch opens, providing power to the normally open contact in CR1, the relay CR1, closing it, and also illuminating the low water light, and at the same time, powering control relay CR2, powering it closed, which then rings the audible alarm, which is the AB symbol also circled in green. All right, so what does this all mean? I mean, why did I take you through the wiring diagram of a standard gas-fired boiler? Well, there's a few reasons. First, it was to show you how AC voltage is applied to a boiler's circuitry. Secondly, to show how reading an electrical wiring diagram is not like reading a newspaper from left to right, top to bottom. The circuiting sequence moves all over the diagram depending on the sequence the BMS is putting it through. So you need to know the sequence to read it effectively. And then lastly, electricity transmission is both complicated and it's dangerous. And unless operating personnel are properly trained, bad things can happen, which not only affect the operation and its reliable uptime, but personal safety too. And that's why companies like we at Cleaver-Brooks and other organizations offer boiler operation and safety courses in our facilities, or your facility, or online. And when it's in our facility, it's hands-on training with certified instructors with years of experience who take the individual from the wiring schematic to various live demo boards where faults are created and the technician needs to find the fault using the wiring diagram so the boiler can be put safely back online. And through it all, safety is paramount, meaning a solid appreciation of what electricity is, how it's applied in the boiler, and what the individual needs to know to safely work around it. It's stressed in all aspects of the courses out there. And it's not just our course, it's all these courses. So I strongly advise, if you're an operator or a supervisor with hands-on involvement and or you're supervising people who are, you seriously consider a solid electrical training course be taken. The internet is full of opportunities. And at the risk of sounding biased, I know that we have an excellent one as well. So here's today's summary or takeaway points. Electricity is the flow of electrons from more to less potential. Direct current is unidirectional and cannot be transformed. Alternating current moves in both directions, above and below the 0-volt horizontal, in a sinusoidal curve. AC can be transformed to increase and decrease voltage. Voltage is the electrical potential difference between 2 points, and also referred to as electromotive force. An ampere is the measurement unit used to determine the flow of current. Watt is the standard unit of power, where a current of 1 amp flows across a potential difference of 1 volt. Ohm's law for voltage is E, or voltage equals amperage times resistance. Neutral is also known as the common, which completes the circuit. Ground is a direct physical connection to earth for safety purposes and should not carry current. Three-phase power is also known as polyphase, with 3 separate current supplies coming into one connector. A schematic wiring diagram